We're going to work on E2, and we have our general scheme right here. We have to know that it's just one step, just like SN2, one step, concerted step. Now, the factors that we're going to use, I'm going to write them here. First, we need a base. And our base in this case is OH minus. Now we can see OH minus as NaOH, we can see other bases, we can see some kind of ionic compound, but the important part is the part that has the minus. We also need our substrate. That is the molecule we're going to work on. In this case is this right here, so I'm going to write it CH3, CH2. And then we need a leaving group. So in this case is the Br. We said that halogens, groups in 6A, they make really good leaving groups. So we got our base, we got our substrate, and we got our leaving group. So everything should be set. Now, this mechanism is going to go like this. Like I said, it's a concerted step. You go, the OH serves as a base. It picks up one of the beta hydrogens, which are slightly acidic. Remember that the carbon that is attached to the Br directly, this is our alpha carbon. Then the one adjacent to it, or the ones adjacent to it, are going to be beta carbons. So the hydrogens attached to the beta carbon are beta hydrogens. So they are slightly acidic. So the oxygen is going to pick up the acidic proton. Then the electrons in this bond are going to come here to form a double bond. And then since this carbon is going to have 1, 2, 3, 4 bonds, something's got to give. So we say the leaving group leaves with the electrons. And the result is our molecule that we added a double bond. An example of E2. We have our molecule here, and we are going to call all of this the substrate, right? We have our leaving group here, and we have our base right here. We see an ionic compound. We know that the only part that's going to react is going to be the base, and the Na is going to be an S spectator ion. So what I'm going to do is I'm going to copy this side right here. So that's step 1. And then this, my Cl right here. Then I know that the OH is the one playing the role here. So the problem I'm running here is that since this is the alpha carbon, the one attached directly to the leaving group, we have 2 beta carbons, one here and one here. So we have a hydrogen on this one and a hydrogen on this one. So now we have to figure out which one of the 2 is my OH going to pick up. So the way we have to analyze this is which one will be more acidic, this one or this one. And based on inductive effect, which alkyl groups inductively feed electrons, we can see that this carbon right here, this whole group is going to feed electrons this way, and this group right here, although it's not so big, but it's still going to feed electrons this way. So it's got 2 groups feeding electrons. Now, this other beta hydrogen, you only have 1 group feeding electrons to it. So the most acidic one is going to be this. Since that is easier to take out, you will pick it up with the base, and then this bond is going to break, is going to make a double bond right here. And we said our leaving group is going to take the electrons from the bond and is going to leave. So what we get is this group right here. We just copy it. Then we copy the chain. And now this bond that came here, it made a pi bond, and you don't see the Cl anymore because it took off with the electrons. So we have our molecule right there. Okay, another example. So we have our molecule here, base, and the product. Now we're going to check if the players are there. We see the base right here, we see the substrate right here, and we see our leaving group right here. So what I'm going to do is I'm going to copy this on this side, and I will do this, this, okay, and then I have my leaving group right here, plus OH minus. But I know it's going to be a base because we're doing elimination reaction. So what's going to happen here is we have a proton right here, which we said the carbon right that is attached directly to the leaving group is our alpha carbon, and then the one adjacent to it, or the ones adjacent to it, are going to be beta. Now you do have a proton here, but based on the product, this is the one that we're going to take out. So what is going to happen is this is going to act as a base, and it's going to pick up this acidic proton. Then this bond is going to make another pi bond right here. And while that happens, this carbon is going to have too many bonds, so the leaving group is going to leave with electrons. So we said it's one step, one concerted step, and what we get is this right here. When this bond broke, it made a triple bond right here, and then we have one carbon here, which is, okay, let's say we have one carbon here, which is this one. This is our beta, which is this one. Then in here, instead of a double bond, you have now a triple bond. You got to think of carbons here. So this one is this one right here. Then you have this one on top, which is this one. And then you have the last one, which is that. The reason why I wrote it like that is because this carbon, these two carbons that are there, their hybridization is sp. So if it's sp, you expect the molecule to be linear, or 180 degrees here, between here and here. So it is going to be linear. It cannot make angles like this one. That's it.